So what we're doing in Chapter 8 is we're using our hypothesis testing and our confidence intervals again in a new kind of situation. The new situation has to do with comparing different populations. So what we'll be working on here today is using a hypothesis test to see if there's a difference in two different populations. Here in 8.4, we're looking in particular at proportions. 8.1 was very similar. We were still testing for differences between two populations, but it was with means instead. So since we're looking at two populations, that means we'll have two samples, and there ends up being two of everything. You can see that in this z-score formula here, everything looks double. It's kind of like double vision. We've got two of these p-hats, two of these p's, two of these n's. Good news is we don't have to worry much about the formula because we've got our calculator command to rely on. So working with proportions, comparing populations, that's what we're all about here today. Let me give you a minute to read through example 1 a couple of times and see what they're telling us and what they're asking us. The basic structure of the hypothesis test is going to be the same as we're accustomed to, so we'll expect to have some kind of evidence from our samples. Because we're dealing with proportions, that would mean an X number and an N number for each of our samples from our two different populations. And then also we'll want to set up some hypotheses to show that we're testing some proportions. Since there are two of everything, what we tend to see is some little subscripts. Like one of the populations is men. So everything having to do with men might have a little 1 next to it. So X1, N1, P1 lets us know all of those are for the population of men. And then the other population are women. So all of those X's and N's and P's would have a little 2 next to them, letting us know those all come from the population of women. So when we're reading through the information, they start talking about a sample from the population of men. It says that there were 50 total in the sample. That would be the value for N. And out of those 50, 44 said they have less leisure time than they did 10 years ago. So X would be the smaller number out of 50 that meet the criteria we're interested in. We should have a similar set of numbers for the women. Might take a second to see if you can fill those in. And then we'll focus on the question. At alpha equals 0.10, is there a difference in the proportions of men and women? So we want a symbol to represent a difference. Different meaning they're not the same. So I'm thinking a not equal symbol, which we know has to go in the alternative hypothesis. So HA in this case will represent our claim. The idea that the proportions are different. So P1 does not equal P2. Then we know the null hypothesis should be the opposite with an equal bar. So that's what it looks like in a two population proportion test. We've got our information organized here for the samples, our evidence, and we've started to set up our hypotheses to get the test going. Seen anything we want to double check about that so far? Well, from that alternative hypothesis, we can still tell which type of test it is. The not equal symbol helps us know that this is a two-tailed test. One of the things we might be asked about is the standardized test statistics. So those are the z-scores that would correspond with our shading here. One negative and one positive. We'll get that from our calculator command. Also from our calculator command, we'll get the p-value, which we can compare with the alpha they gave us. They said that they wanted alpha to be 0.10. So that's where the 2-prop-z test comes in. We'll want to go back to our stat button, back over to the tests menu, our new favorite place. The one we're looking for is 2-prop-z test. On my calculator, it's number 6. That should all kind of sound right. We're talking about a hypothesis test, so that's why it says test on the end. We're using the standard normal z distribution, so that's why there's a z in the middle. We're looking at proportions, so that's why it starts out with prop. And we're comparing 2 populations. That's why we have the 2 at the very beginning. So we're looking for 2-prop-z test. Might be number 6 or somewhere very close to that. And we want to put in our numbers, like the 44 out of 50 for x1 and n1, the 48 out of 50 for x2 and n2. And let's make sure that we represent the alternative hypothesis here. We used a not equal symbol, so we want to make sure not equal is selected. And go on down to calculate. Anybody need a little help with the calculator work so far? So the z there on the top row, that would be the standardized test statistics we might get asked about. Looks like there would be a negative and a positive 1.47. This was a homework question. We might need to list them both with a comma between. And then we want the p number. That's going to need to be rounded. Let's say they asked us to round it to 3 decimal places. So maybe a 0.140. Everything from here on out is exactly the same as it has been in Chapter 7. We want to compare and use that to make our decision about the null hypothesis. And then that will help us know what wording to use in our final conclusion. Let me give you a minute to think about how we're going to finish this off. Looks like the p in this case is bigger than the alpha that they gave us. So that helps us know we should not reject HO, fail to reject the null hypothesis. So failing to reject the null hypothesis means we're going to stick with this. And that is not the claim. So it looks like we don't have enough evidence to support our claim. We could say there is insufficient or not enough evidence to support the claim. The claim that there is a difference in the proportions of men and women. Remember, our flowchart can also help us with that decision and conclusion. The claim was next to AJ, so we'll start by moving down. Then P was greater than alpha. So we're on the very last row here. These two bubbles will help us with our decision and our conclusion. So that's why we failed to reject HO. And why we said there's insufficient evidence to support the claim. Anything we could help out with that first example of a 2-prop Z test? Well, let's take a second and see. In the end, did we decide that these proportions are the same or are different? Let's see. We said there's not enough evidence to support the claim that they are different. So we're leaning more towards saying they're the same. If two numbers are the same and you subtract them, do you know what you would get? If two numbers are the same and we subtract them, we should get 0. I mentioned that because in the second half of the lesson, we'll see a way to figure out how different they are if there does turn out to be a difference. In this case, because there didn't turn out to be a difference, it wouldn't be very interesting. They would be roughly 0 apart because we determined that they weren't different. But that's the other piece of the puzzle we'll be looking at in a few minutes. Before we get into that, though, we'll practice another hypothesis test. This next one is just slightly different because the information's given to us in a little different way. Instead of giving us the raw numbers like 40 out of 50, we have a percentage instead. If you see anything you'd like to double check on the front page before we try another one, let me know. If it's seeming okay so far, then we'll be ready to try example 2. And the bar chart down here that goes with it is the part I was mentioning that's a little different. We've got percentages to work with. So be sure to keep that in mind as you're reading through the problem, figuring out what they're telling us and what they're asking us. I'll let you get started. If you need any help along the way, let me know. If you happen to be seeing a different example, it may be because I updated the notes a week or so ago. Something changed in the homework and I wanted to make sure we were ready for it. So reprinting the newest version on Blackboard could help. Well, are you noticing what I mentioned about the percentages? They do come out and tell us that 1,044 adults were surveyed from country A, but they don't give us the exact number for X. We're going to need to calculate it using this percentage. What we do know is that 52% of this 1,044 favor building new nuclear power plants in their country. So if we can figure out what 52% of 1,044 is, we'll have it. We'll want to think of 52% as a decimal, and for of, we'll multiply by 1,044. One thing that we need to keep in mind here is this X needs to be a whole number. So let's don't put that decimal down. Let's round it to the nearest whole number. So 542.8 would round up to 543. In other words, those X numbers might need to be rounded. They should be whole numbers. We'll need to do the same kind of thing for country B. Give you a second to work on that. So all of the given information and setup is on the screen now. You might want to check in and see if we're getting the same things. Then you'll be ready to roll on your hypothesis test. Is anybody needing a little help getting started? So you might check and make sure we have the claim in the same place. Since they wanted to know if the proportions were the same, the claim would be the null hypothesis with the equal sign. Then I have the numbers from the calculator. Our standardized test statistics, I rounded to 2 decimal places. And our p-value, I rounded to 3 decimal places. Anybody need a little help with the hypotheses or the calculator work? Well, I could use your help then. When you're ready, filling in the decision And knowing what words we're going to put in these blanks in our final interpretation or conclusion. So when you're ready, let us know what the decision should be in this case. I'm seeing a fail to reject HO since our p-value 0.16 is greater than the alpha they gave us of 0.06. Sounding good? So if we fail to reject HO, here's HO. Since HO is the claim, then we're failing to reject the claim. So there's not enough or insufficient evidence to reject the claim. So remember, that has to do with the fact that HO was our claim. So on our flow chart, we're going upward to start. And then we saw that the P was greater than alpha. So we end up in the second line. That's how we knew to fail to reject HO, and how we knew to use the words insufficient and reject. I'm seeing a couple of different things on Teams. If anybody has any questions, needs a little help getting that final wording just right, let me know. So if we did not reject the claim, that means we stuck with this null hypothesis. So we essentially think the proportions are equal or the same. And like we said a minute ago, if they are equal or the same, if we subtract them, we would get 0. So if they are the same, there would be no difference. We get a difference when we subtract. And I mentioned that again because when we flip the page, we'll be using confidence intervals to figure out what that difference is. In problems like we've seen so far, it's not overly helpful because we already know that there's no difference. But if we had decided there was a difference, the next reasonable question might be, well, how different are they? Are they 2? Are they 5? Are they 200? Are they 5,000? How far apart are they? Anybody need any help on example 2 before we check out that confidence interval business? All right. Well, remember, we're seeing everything double. So this confidence interval formula is pretty crazy looking. Confidence interval formulas are already quite big, right? Because we have the top and the bottom number that's being calculated. In this case, to represent the difference, like we were talking about, if you subtract one of these proportions from the other, we want to know how far apart they are, how different they are. So double vision in the confidence interval formula. which is not a big deal to us because we have this calculator command we can rely on. But what we're doing essentially is we're finding a range of how different the numbers are. So just say, for instance, we plug some numbers in here and maybe we got 10 for the bottom and 20 for the top. We would be saying that those proportions are somewhere between 10 and 20 apart or different from one another. So we're coming up with a range for how different the proportions are. Well, back in example 1, you might recall, we determined that the proportions were not different. So down here where it says, let's revisit example 1. If we're calculating how much the proportions differ, knowing that we determined they weren't different, it should be somewhere around 0. So when we calculate this confidence interval, I think we'll find that the lower number is negative and the upper number is positive. It's going to be centered or hovering around 0. Let's try it out. So the command we're going to use, starting with stat, over to tests again. It looks a whole lot like the one we just did, but this one ends with int instead of test. We're still looking at two populations, comparing proportions using z, but this time a confidence interval instead of a hypothesis test. For me, it's on the second screen next to B in the list. So we can cruise on down there. Enter to select it. And since we're going back to example 1, let's type in those numbers again. We had 44 out of 50 for the men and 48 out of 50 for the women. One other thing we'll want to notice was alpha in that problem was 0.10. So alpha 0.10, what confidence level would that correspond with? Because the calculator wants a confidence level for our interval here. In other words, if there's a 10% chance of making a mistake, how can we turn that around and say how confident we are? 10% chance of making a mistake means we're 90% confident. Yeah. So we do want a 90 next to sea level there. And when we calculate, see if we don't get a negative and a positive because it's hovering around 0. Like that negative 0.168 and that positive 0.008. So not surprising at all because we didn't think they were different. The difference when we subtract should essentially be 0. If there was a difference, then both of the numbers would have the same sign. Maybe they would both be positive, or maybe they would both be negative. But one positive and one negative justifies what we thought. They're not different. If we subtract them, we're pretty much going to get 0. There's another example where we need to use the confidence interval right below. I'm pretty sure I copied and pasted this one from homework. So it will help us make sure we're ready. Let me give you a minute to start reading it through, thinking about what the x and n numbers would be. Let me know if you need any help. Looks like another instance where we're not given the raw numbers, but we have a percent instead. So we'll want to think about changing that to a decimal. Dividing by 100 or moving the decimal 2 places to the left is a good way to do it. So for 9.7% of 1,068,000, we would multiply 0.097 by that big number there. That one didn't need rounding, but remember we do want x to be a whole number, so if it turned out to be a decimal, we would need to round it according to the decimal. For 9.2%, we want to think about using 0.092 times its total number. So along with the confidence level that they gave us, we should then have all the numbers we need. And let's say we were asked to round to 3 places. I'm coming up with 0.004 and 0.006. Anybody need a little help with the calculator work on that one? So remember we said if they have the same sign, that means that there was a difference. And now we know exactly how different these proportions are. They're somewhere between 0.0046 and 0.004. Can see that that's kind of centered around 0.005. So pretty small numbers. They're just a tiny bit different.